Let's start off looking at this guy. We got a lot of problems like this where we have block one, block two. Um, let's just go ahead and throw friction in as well. We're dealing with that. So here, but now the pulley has mass m and radius r naught. So it's going to have a moment of inertia, and well, we have to take into consideration. So here, just like with the problems we did before, we were finding the tension, the system tension, and the system acceleration. So determine well, actually, yeah, system tension and well, one thing to note is that whenever we consider uh, the mass of the pulley, now the tension on either side of the pulley will not be the same. Okay. And do something about this glare real quick. It didn't do much difference, did it? Mm. You know what? That made a difference. All right. Okay, sorry about all that. I just gotta go back to the way it was. All right, I'm just going to move on. As I was saying, the tensions on either side of the pulley now will be changed because moment of inertia affects the tension, and we didn't have to worry about that whenever we had a ideal pulley, where an ideal pulley basically had no mass, so it had no moment of inertia. So when we diagram this problem now, we have to take that in consideration. There's a T2 here and a T1 here. So on this object, we're going to have T2 up and T1 from the center of mass in this direction. So they're not the same tensions anymore. We still have a normal force here, and we've got gravity, M1G, gravity here, M2G, and we'll go ahead and put friction in now as well, and we have a frictional force here, F. And so let's say what's known is the coefficient of friction. So we're given M1 yeah, just missed them all here. M1, M2, coefficient of kinetic friction, of course, the acceleration due to gravity. And I think that's all we need. Yeah, so there's no angle there, so we don't need that. Oh, and of course the masses. So we have the mass of the pulley, which I'll call capital MP. MP. And the radius of the pulley, R naught. Or RP, R naught or RP. I just do R naught. So what we're trying to find is find T1, T2, and the acceleration of the system. Now still, the acceleration of each block will be the same, but because the blocks are in tandem. One thing I can add to this actually is, since this is the linear acceleration of each block, but that's related to the angular acceleration of the pulley. So we could go ahead and put that in, find the angular acceleration of the pulley. So now, whereas before we had 2 unknowns, now we've got 4 unknowns. And the 4 equations that we will use to solve this, well, there's one equation that relates A directly to alpha. That's pretty easy. So that equation is A, the linear acceleration, is equal to R naught times the angular acceleration. Since we have R naught, once we find the linear acceleration, or we could find the angular acceleration, or vice versa. But then the other 2 equations are going to be, other 3 equations are going to be Newton's law for X, Y, and also for rotation. Newton's law for the X direction is the net force. Well, in the Y direction here, there's no acceleration, so it's the first law. So the Newton's law in the Y direction is equal to 0. In the X direction, we have the net force equals mass times acceleration in general. We have to apply that to each block. But now on the pulley, we also have the net torque equals the moment of inertia times the angular acceleration. So those are basically the so we have four equations, so four unknowns, so we have to have four independent equations. Those are the equations that we're going to be using, and that will give us a system of equations that we can then solve to find for all of our unknowns. In fact, this is kind of like a brief summary before we do the problem. So I'm going to put these as numbers like this. And then we can start. Okay, so that's for all of these blocks in tandem now, we've got this third equation in here. Well, actually this guy and this guy to relate with our rotational motion. So let's go ahead and do the problem. And then I'm going to have you do one. I'm probably going to give you time to kind of work on it on your own because I want you to kind of work through it a little bit. Because we've done all these before. We did it with no friction. We did it with friction. Now we're doing it with friction and the rotation of the pulley, as I promised you back then we would do. So the first two equations, they go like this. Start with Newton's first law. And again, remember we're superimposing a coordinate system like, yeah, I don't know what happened in my other, I need other marker. I'm missing a marker here, orange marker. I really need it. I have no idea what happened to it. So frustrating, man. This place tonight. Let's go turned upside down. Let me just see if I can go find one real quick. Right back. Ugh. All right, no luck. Just keep rolling. All right. Oh, well, I want to make it black then. We've got a axis like this. X. That's Y. And remember what we do is we project it over the pulley so that down here, X is down and Y is to the right. So that the acceleration for each block is still along the same coordinate direction. In this case, that would be the X direction. All right. So in the Y direction, for block one, we have that the net force is equal to 0. So the forces that we have along the Y direction there are normal force minus m1g equals 0, so that the normal force is equal to m1g. That's a result. We'll need that for friction. Now in the Y direction, the net force, sorry, in the X direction, the net force equals a mass 1 times acceleration. Now we got two forces, tension, T1, and the frictional force. Tension, T1 is greater because the acceleration is to the right, so that means that T1 obviously has to be greater than F. So T1 minus F equals M1A, but F is equal to mu K times N was M1A, but N we just determined was M1G. So putting that in, we get T1 minus mu K M1G equals M1A. So that has two of the unknowns, T1 and A. Okay. Let's now go on to this guy, and we'll do the pulley last since that's new. But this guy, acceleration is down, M2, G is greater than T2. So for this one, we're going to have M2, well, let's start with Newton's second law. Net force equals M2 times A. All right. Now, net force is M2 G minus T2 equals M2A. And that's as far as we can go with that. And that just comes straight out, and we got that guy in there. The T. So we got three of the unknowns, T1, T2, and A. But we still have to, we've got this guy. And here, we can apply Newton's second law, but in terms of rotation. And that's this equation. So you got two torques, clockwise and counterclockwise. This guy tends to make it want to rotate in the clockwise direction. This would want to make it rotate in the counterclockwise direction. But this is a greater torque. So overall, it's going to rotate like that. It has to in order for the thing to go down. So you can say here, the net torque equals I, the moment of inertia, times alpha. But now you have a torque associated with this. Now you're going to assume that, remember, torque is R cross a force, R cross T. So basically, like this torque, remember, this is R here, R not. So you're going to have actually, technically, so it's kind of exaggerated, but the angle is going to be 90 degrees. So it's more like the torque is the ideal torque extends from that point. So like if this were kind of a better circle, I should probably inside you could see like yeah, do it smaller. That is actually something like that. So that the tension actually is you're getting a 90-degree angle from the radius on both of these. I know it's not a perfect, but it's 90 degrees. Doesn't make a perfect, kind of off a little bit, but that's 90 degrees there, and this 90 degrees here. So the torque is just going to be tension times the radius times sine of 90, which is 1. So this torque will be the clockwise torque. So we're going to have T2 times R naught, and then minus the torque in the opposite direction, T1 R naught. And that equals the moment of inertia. Now you can assume that the moment of inertia is for a solid block, a solid cylinder with the axis of rotation through the center. And I think that that is it 1/5 mr squared? We can look it up. I'll go ahead and put the I down. So I times alpha. But let's look up the moment of inertia for a solid cylinder. And we can find it here. I got the book there somewhere. Here's a book. Yeah, so we go for solids. We looked up those moments last week. It was in chapter 10, I think they are. Moment of inertia. What's the deal? I was just not doing it. Okay, start over there. A solid cylinder is going to be, this would be a shorter L and it would be like a disc, a solid cylinder. So that's actually, wow, I can't even see it. 1/2. And the vision is getting worse. For a solid, that's a solid cylinder just about central axis. Yeah, that's 1/2 mr squared. So that would be a solid cylinder, yeah. So 1/2 is actually 1/2 mr squared. Okay. So that's the moment that we would have to use here, 1/2 mr squared. So I'm gonna we'll come over here and we'll say that 12I is equal to 1/2 MP R naught squared. And the alpha is R naught times alpha, which, well, actually alpha is A divided by R naught. So if I substitute 13 and 12 into 11, then this equation becomes T2 times R naught minus T1 times R naught equals, it'll be 1/2. Guess I'm running out of space, aren't I? 1/2. Hmm. I'm not gonna have enough room there. So I'll come back over here. Unless I can make this work. I can make it work like this. Okay. 13. So we're gonna have T2 R naught minus T1 R naught equals I, which is 1/2 MP R naught squared. So 1/2 M sub P R naught squared. And then, as I said, if I solve this for alpha, this becomes, times A over R naught. Actually, this is squared. So 1 R naught cancels here. I get 1 left here. And that becomes T2 R naught minus T1 R naught equals 1/2 MP R naught is left. And then I have an A. Now, out of that, all the R naughts cancel. That goes, that goes, that goes. So this equation is left with T2 minus T1 equals MP over 2 times A. And so that gives me my equally determined result. So I've got 3 unknowns, T1, T2A, and 3 equations that I'm going to use to solve, namely equation 7, equation 9, and equation 15. I can solve those simultaneously. So basically, I take equation 7, substitute it into equation 15, solve equation 9 for T2 and substitute into equation 15, and then solve for A. Once I have A, then I have to go back and put that in to get the analytical solutions for T1 and T2. So I want you to work on that. I want to give you some time to work on that. And everything we did was basically the same as before, except starting with equation 10. This was new because we're incorporating the pulley as I promised you we would. So, yeah. Now, one thing I want to check here before I give you some time to work on it, and I might have had a sign error here, possibly. Um,
Dr. Gamble,
yeah.
why is there an arrow with an X beneath it under M2
Can you tell me what equation?
uh in the um in the diagram?
Arrow with an X under M2. This is M2. You talking about this?
No, right below that.
This? So that was representing the axis. So the x-axis was pointing to the right, and I took it over the pulley, so the x-axis is pointing down and the y-axis is pointing to the right. Just to remind you that that's the convention that we were using
Okay,
from
thank you.
before. Does that make sense? You remember that?
Yes.
Yeah. But maybe I should erase it because I didn't have a color, a separate. Usually I put it on the picture, but I didn't have I've run out of an orange color for some reason. I didn't. Yeah, whatever. So go ahead and do that because I want you to work through that. And but let me just think. I think this sign is right. Mm. Technically, the torque is into the board, but into the board is the negative z direction. But well, I'm just going to work through it. In the end, it'll work out. I can figure out in the end what the solution by the solution if I did that right. All right, so go ahead and work on that a little bit. Be right back. All right. You knock this off for you, and then I'll set up another one. So my method would be to substitute equations 7 and 8, or 7 and 9 into 15. I have to adjust 9 a little bit. So T2 T2 is going to be equal to from here M2G minus M2A. So basically putting 16 and 7 into 15 gives the following equation. Okay, so T2 is going to be, I don't think I have space over there, do I? No, I have to redo that. So T2, mm, so T2 is equal to M2G minus M2A, and then T1, so there's a minus sign here, but then we have T1 minus mu K MG, M1G, M1A. So when you put the minus sign through, let's drop this down a little bit. So we have minus T1 plus mu K M1G, and sorry, I know what's going on with me today. I'm substituting in T1, so T1 actually equals M1A plus mu K M1G. So when I substitute that in, I'm going to have a minus M1A and a minus mu K M1G, and all of that equals MP over 2A. Okay, so that's 16 and 7 into 15. Just check that math real quick again. Okay, now I'm going to factor out a G from these two terms and take this stuff over the other side. So I'll have M2G, or at M2G and minus mu K M1G. So M2 minus mu K M1 times G is equal to, over the other side, I factor out an A, I have A times basically M1 plus M2 plus MP over 2. So that in the end, my acceleration A is going to be equal to G times M2 minus mu K M1 over M1 plus M2 plus MP over 2. Actually, the whole thing. Yeah, so that makes sense to me. I think I got the minus sign right. All right, so that's acceleration. And you see that when mu k goes 0, then we reduce back to the situation we had before. And the only difference is now that the moment of inertia of the whole system is increased because you have the inertia term for the pulley in there. Um, yeah, so I think that's I had a question about this equation, whether I had the sign right, but I think it's because I guess there's two minus signs. There's two minus signs because right? Because I have a good explanation, but it's kind of throwing me off still. I know it's right, but it's not the justification. Because when you set up a coordinate system, like, I wonder if when y is in the way that I have done so, then negative z x, no, positive z is out of the board. But the angular acceleration is definitely clockwise, so that the rotation is clockwise, so that it's along the negative z axis. But if I make, yeah, I think there's two negative signs. Is how you do that, because I would have the net torque is equal to a negative acceleration. So then this would be a negative, actually it's right here, a negative T2 R naught plus T1 R naught equals a negative I alpha. That's right. And because this sign has to be in the same direction as this guy, so it would be two negative signs. So then when I multiply through that negative sign, I just get that equation there. That's right. That's it. That's why it doesn't. It's okay. So we're good. Okay. So but now we want to take that. I'd like to go ahead and do the tensions as well to show you that there's a little bit of a difference than in previous problems. So we'd have to take this acceleration, and to get T1, we put it back into this equation. And to get T2, we'd put it back into this equation. Um, and we could compare those back to the regular the tension whenever the pulley was 0. And I think what we're going to find is one is going to be greater than that tension. I think it'll be T1. T1 is going to end up being greater than when the ideal pulley was like that, and T2 is going to be less. But both of those should reduce back to T whenever there's a term in it that goes, I guess the friction term will be in there and it should go out. Oh no, there'll be a moment term whenever the mass of the pulley is 0. That will go back. And this does too, actually. When this mass is 0, this acceleration goes back to what it was before when we had the ideal pulley. And by the way, you can see that the acceleration has decreased because the numerator has increased. The previous numerator was, well, the previous solution was just g times m2 minus mu k m1 over m1 plus m2. But when we add on an mp divided by 2 to the numerator, it decreases the overall acceleration, which you would expect. Because if the moment of inertia if the inertia of the system increases because we now are including the moment of inertia of the pulley due to its non-zero mass, then everything being the same, you would expect that the acceleration of the system would decrease. So it does. By the way, if I just divide G by R naught, this gives me alpha per this equation here. So alpha and A are just a constant multiple of one another. What constant? The radius of the pulley. So I'm going to go ahead and substitute equation 19 into equation 1 and then solve, and we'll see what we get. I don't think I need this anymore, so I'm going to go ahead and erase it because I need the space. I'm going to leave that though. Okay, so T1, if I put this guy in there, so I'm going to get, call this equation 20. So T1 minus mu k m1g is equal to basically A times that. So that's just an m1 times all that. So that's going to be m1. Actually, I can go ahead and work kind of, I'm going to, so m1 times this guy, I'm taking the g out. So I have a g, but then I'm going to have m1 times m2, the first term. Second term is going to be minus mu k m1 squared, and I'll keep that. So over m1 plus m2 plus mp over 2. This term has got to come over. When that term comes over, I'm going to, so t, that's going to be equal. So the g is going to factor out of both of those terms. So g, and then in brackets I'll have, well, this is going to be a mu k plus mu k times m1, but I need the common denominator, which is this, and then that multiplies that times that, so it gives me 3 terms in addition to those 2 terms. So the common denominator will still be m1 plus m2 plus mp over 2. Now the 3 terms I get here are going to be m1 times m1, which is m1 squared, then plus m1 times m2, and m1 times mp. So m1 mp over 2. And now these 2 terms are left, plus m1 m2, and then minus mu k m1 squared. Oh, I left off, there was a mu k on this. Oh, let's do all that over again. I forgot the mu. It's not just m1 times those, it's mu k times m1. So again, m1 plus m2 plus mp over 2. So the first term is going to be mu k m1 squared plus mu k m1 m2, and then plus mu k mp over 2. And now these 2 terms left, which is just plus m1 m2, and then this term, which is minus mu k m1 squared. So that looks better because now I can see that um, this term cancels with that term. You expect something like that. Now, the rest of this I can factor out. Drop the M1 here too. That was going to be a mu k M1 times M2. So, we can simplify this 22. Yeah. So G times, well, what we have left is M1, M2 plus M1, M2 mu k plus M1 mu k M1 MP over 2. 1, 2, 3, 1, 2, 3. And then all of that over M1 plus M2 plus MP over 2. I don't know if there's, uh, yeah, I think I see a way I'd like to do this. But keep that there. And so I want to keep this formula here because, well, just so I don't forget what the acceleration is, I'm going to take that and put it over here. So the acceleration, equation 19, acceleration A is equal to G times M2 minus UK M1 over M1 plus M2 plus MP over 2. And I want to go ahead and erase all this. Oh man. Okay. So do it in steps and factor out an m1 times m2. Let's see what I can get this down to. So G, and so this is going to be, I'll put that in brackets. So we're going to have an m1, m2 over m1 plus m2 plus mp over 2. I factor that out, and what I'll have left, I guess I don't need this then. What I'll have left is there's a 1 here, there's a mu k there, and over here there is a, yeah, so 1, there's a mu k, and here it's got to be friction, it's got to be a unitless number. So we have the mu k, we have the 1 over 2, but here, and the mp will still be there. The m1 got factored out, but I have to now divide by an m2. So I think that when you multiply by through m1 times m2 times that term, the m2 cancels and you have the m1. So that's right. And that is consistent with what you should get because this is unitless, because mp over mp is unitless. So all those terms must be unitless since mu k is unitless. Yeah, that's it. That's it. And you can see, although is that counterintuitive? Yeah, I thought that, I think it's going to be larger, I guess, because, or maybe they both are larger. Maybe they both are. I thought that one would be larger than T and one would be less. But here, when MP goes to 0, that goes back to, that's definitely increasing the tension because, well, it's decreased. Oh, my bad. No, no, no. That's larger. That is larger than the tension because when this is 0, then, well, I said it would be less, but it's actually larger because of plus sign here. So this is the force whenever there's no pulley. Also, this term has to go to 0 as well. So I have to be careful about that. But so I don't know. It definitely, I don't know that, but that reduces it. So I don't know. I guess you have to put in the numbers to see. It's kind of hard to it- gauge what it would be with MP not having being a numerical value. But I'm confident that that's the solution for T2. Now I'm thinking that T1 is just going to be that same thing, but there'll be a minus sign here and an M1 there, I believe. But let's just go ahead and do it. So what I have to do is plug A into here. Oh, wait a minute. Why is that? Oh, because that's T1. So it is what I thought. That's T1. I had a miss. I somehow went from T1 to T2. That's T1. And that is what we were solving for. Okay, so yeah. So that's what my intuition led me to believe that T1 would be greater than T for the ideal pulley. There is a possibility that I didn't think of that they're both greater, but that this is greater than T2, but T2 is still greater than, what it would be without pulley. That's a possibility. And I definitely think we're going to minus sign here and one there, but it's going to be hard to gauge unless you put in numbers. I can't. Yeah. But anyway, let's just go ahead. So now we're going to put A into here and then do the same thing, and we should get something similar, but for T2. All right, so going from 16 to 19 over there, we've got so 19 into 16, we will have T2 equals M2 G, and then minus M2 times all of that. So again, you're going to have the minus G times, well, since I'm not going to take the common, I'm going to do the common denominator in the next term. I should keep that plus. And then over here, you will have quantity minus M2 squared, and then minus and the minus is a plus, UK M1, M2. And then, of course, over the denominator, M1 plus M2 plus MP over 2. Now, finding the common denominator between that term and this term is going to be the denominator here. Factoring out the G, we've got G times, I'll put this in brackets, common denominator, of course, is M1 plus M2 plus MP over 2. Then M2 times this guy is going to be M1, M2, and then plus M2 squared, and then plus 1/2 M2 MP. Now these two terms, minus M2 squared and plus mu k M1 M2. Okay. Now doing the same type of simplification. Looks like it's panning out to what I suspected to be the case. So T2 then, we'll leave the acceleration there because that's one of the general solution. Um, Factoring out the M1, M times M2 again. So we'll have this term out on the front. So we'll get, oh, by the way, the M2 squared cancels. That goes and that goes. So we're going to still be left with 3 terms, just like we did here. But we'll factor out the M1 over M2 and the denominator. And so T2 T2 is equal to G times M1, M2 over M1 plus M2 plus MP over 2 quantity times um, 1 plus mu k, and then in this case it'll be plus MP over 2M1, what I thought. But it's still a plus sign. I guess it's just a different term. So I guess they're both going to be greater. So that's not what I expected. I thought one was less, one was less and one is greater, but no, they're both greater than the tension force whenever. I guess that does make sense because the total moment of inertia increases. Yeah, that's interesting. So you're going to get this. You're going to get 1 plus mu k, but then plus um, basically mu k over 2 times mp over m1 as opposed to mp over m2. And as I said earlier, both of those results, 23 and 26, reduce to the tension whenever the same tension force whenever the pulley is ideal. And that tension force, so ideal case, in fact, we can see it from here. The ideal case for the acceleration is going to be G times M2 minus UK M1 over M1 plus M2 whenever ideal case basically MP goes to 0. And up here, the tension force is going to be equal to G times M1 M2 M1 plus M2 MP over 2 and then times a quantity 1 plus mu k. So no, this is 0. So this is just M1 plus M2 and then over mu k, period. So you can check back in your solutions and see that those were the solutions that we got whenever the ideal pulley was that case, whether we had the ideal pulley. But now that we're taking the moment of inertia in, we've got terms in the denominator of this 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 mass ratio thing. By the way, this is not unitless. It's kilograms in the denominator, but kilograms squared in the numerator because mass times mass, which is what you should get because tension is acceleration times a mass. So you got the acceleration term here, the mass term there, and a unitless term here. But again, this is greater because T is greater because you're adding on something to this quantity here. And yeah, so it's not negative there like I thought, it's positive, and they're both greater. And yeah, this term is decreased a little bit, but I think you find overall that it's still, when you multiply all that in there, it's still greater um, than than this guy. I guess you can tell though which force is going to be greater. I guess this force is, well, we don't know. It depends on the ratio of masses. It depends on whether M2 is greater than M1. Mhm. And also depends on the coefficient of friction. Yeah. In general, though, well, yes, well, that's all you can say. That's what I'll say. Ah. Mm. Well, they become involved problems very quickly. And the next thing to do would be to put that object at an angle, and then do the problem again. And you got two options there: angle up or angle down. We did both. I would do them all, if just to practice. But you can use these solutions as the base. Basically, this will be the base solution for all of them. But now you're going to have some other term in there associated with the angle, or somehow it's going to pop up. I think there's going to be an angle associated with this term. Is what will happen. Yeah, this would be like mu k times sine of something, or cosine of something. And then when that angle reduces back to zero, should reduce to this uh, solution. But what I'm saying is, go ahead and put in. So now, you do something like this. You have a theta there. You have m1, here, and of course the pulley is here, and then now m2 there. So you got this scenario now. So now, again, T1, T2, T2, T1, and MG is going to be straight down. And of course, the friction is up the plane. And of course, now that no longer ideal, so this is R naught or RP and MP. So, it just goes on from there. Is anybody in class? Anybody there?
Yeah, I'm here.
Oh, is that right? Yeah, Raheem, how you doing?
Good. How are you?
Good, good. So yeah. I'm good. I'm good. I had a good holiday. How was your Thanksgiving?
Good, good.
That's good. Well, yeah. There's that's that scenario. That I there are a lot of problems we could do. We could do that one, then we could angle it down, then you can put the other two angles there. Other to put two a double angle. Something like that scenario where you have two different angles here and here. I'm not going to do those in class, but it just gives you a lot of opportunity to kind of work through and get a gauge of how to use moment of inertia. And I found those problems to be very good in terms of baking that in. So yeah. Now I took a little break. I went over there over the break. I went going over the break now. Probably going to take another little break here, but I want to I want to kind of set up what we're going to do. After that. I guess it's angular momentum is defining angular momentum and then deriving the conservation of angular momentum. And just various other problems in applying Newton's laws with rotation. And we also can get into have to define we've already done kinetic energy, and we have to look at work for angular work conservation. And then statics problems. Some more statics problems where we combine, just continue to combine linear Newton's laws of translation with Newton's laws for rotation for various types of problems. Okay. All right, so I'm going to take a little break there, and then we'll come back. I guess the first thing I'll do is take another look at Newton's second law for rotation, and then write that. So we have one version: net torque equals moment of inertia times angular acceleration. That is equivalent to net force equals mass times acceleration. However, we had a second version of Newton's second law. We said that net force also equals the time rate of momentum. And out of that expression, the definition of momentum, we got that. Well, we can do something similar where we manipulate Newton's second law for rotation, and we end up getting this term where there's a derivative of a quantity that we would identify as angular momentum. And so there's parallel concepts there, or analogous concepts. So we'll do that when we come back. But I would encourage you to maybe try, one or two of these on your own, just to bake this in. And there's a lot going on here, a lot of moving parts, so it could really cause you to really solidify the understanding of how to apply Newton's second law for rotation in conjunction with Newton's second law it's just Newton's laws, basic first and second for rotation and translation. All right. Any questions before we break? So, so starting with Newton's law, Newton's second for rotation. We have the net torque of the system equals the moment of inertia times the angular acceleration. Now, if I I guess what I want to do is I'll do this from my memory. So that's going to be m r squared in general, and this guy is going to be a over r in general. So that goes. We have m r times a But now, this derivation here is, this is so this is m r times the time rate of change of v, right? Yeah. So now, if I take the m on the inside, then I have r times d dt of mv. Now, of course, we know by definition that mv is momentum, linear momentum. Linear momentum. We defined that a while back. So P is defined as mass times velocity. So we can substitute that in. That the net torque is equal to R times the time rate of change of the linear momentum, P. Now we'll just go with the magnitude. I guess I could put that in that guy. All right. Now, oftentimes when we're in rotation, we've been keeping R constant. So for example, if I have an object that's twirling around, now technically the radius, the radial vector is the perpendicular distance. I guess another way of doing this is if I put this object on the ground, well, actually, the example I have been using for you is taking an object like this guy and just twirling it, right? So you put it here and you twirl it around like that, right? So if you think about a mass at a distance r away from the axis of rotation, that distance r isn't changing. So if we were to sketch a version of this from the top down, this picture looks like this. So this is the axis of rotation. The object is spinning. Radial vector r, here's the mass m, and it's mapping out a circle like so, but the radius of that circle doesn't change. So we definitely have an m, on momentum, an mv, right? Because the tangential velocity is here. So you could call that just the momentum. P is always tangent to the path. So, and that can change. So if that's changing, if that's constant, then, of course, but if it's changing, like the momentum is slowing up and slowing down and speeding up because the velocity is slowing down and speeding up, then, this describes that scenario. You could think of orbital motion, assuming circular orbital motion, as this scenario. Although, I guess we assume constant velocity when we assume that for orbital motion. But in fact, the motion of the planets is elliptical. The moon is elliptical. All orbital motion is elliptical. It has to be. That comes out of that's one of the properties that comes out of the universal law of gravitation. But that said, if it's elliptical, we also know, well, you should intuitively know, well, maybe you don't, but the velocity is not constant. It will never be constant on that. It can't be. Well, if there are no external forces, then the velocity will change. And like when you get closer to, like if you have an ellipse, you do intuitively know this, I think. But let's say that, if you look at our sun, well, this is an exaggerated ellipse. It's not this exaggerated, but basically, let's say this is an elliptical path of the Earth around the sun. And this is the sun, for example. So as the Earth goes around, when it's at its apogee, farther away, it's going slower. When it's at the perigee, it goes faster. So there's kind of a whipping motion around. So the whole time, though, the velocity is changing. Once it passes the perigee, it starts to slow down. and it continues to slow down, not necessarily at a constant rate, until it gets to the apogee. And after it passes the apogee, it starts to speed up and then whips around and then, does the same thing. So the velocity is never constant. So you definitely have a time rate of change of the velocity and the momentum. But the thing is, r in this case for an ellipse also changes, because r is the distance that you are from the sun at any time, and that clearly changes as you're going around, clearly. So, and it's not necessarily changing at the same rate as well, right? It's not a constant rate at which it changes. So basically, r can come inside of this operator, and so yeah, we bring it inside. So we have that the net torque is equal to um, the time rate of change of rp. So, and the other thing is that both of these are vectors. So since they're vectors, we have to decide whether the product is a cross product or a dot product. We can't just multiply them together indiscriminately like we did back in high school or before calculus, I'll say. Some of you had calculus in high school. Turns out it's a cross product. And so we say that the net torque then is equal to the time rate of change of this quantity R cross P. Now that quantity has units of meters, kilogram meter squared per second. And it has a definition. It is defined as the angular momentum. So the P is linear momentum, right? Linear, but the MP, the R times R cross P is angular momentum. And we give it the symbol L, small l for individual particles of the system, capital L for an entire system of particles. But here, so we'll say that L, the angular momentum, is defined as R cross P, and the magnitude of that is equal to R, the magnitude of R times the magnitude of P times the sine of the angle between the two. And there definitely would be a like in the case of circular motion, that angle is always 90 degrees. But in the case of elliptical, or true orbital motion, no, it's not. So the theta is also changing. So all these quantities are changing in in uh, in orbital motion, RP and theta. In fact, I'm gonna go ahead and use a phi for this. Doesn't matter, but I just want to do that. So yeah. So that's angular momentum. And it's a vector quantity. Its units are kilogram meter squared per, sorry, just meters per second, kilogram meters per second, kilogram meter per second. It just comes out of the, no, sorry, it's actually kilogram. What? No, I'm right. It is meters squared per second. Kilogram meter squared per second, right? Because units of meters and momentum has kilograms, but also meters per second. So it's meters times kilogram meters per second is kilogram meters squared per second. So it doesn't have a name. There's no particular name for the units associated with, there's no proper name associated with angular momentum. It's just that, it's just kilogram meters per second, vector quantity, and has all the properties of the vector. And you have to, by the direction, you get the right-hand rule. It's abides by the right-hand rule, the run-rat point. We still have that in play. That's all the properties I can think of at the moment. Yeah. So angular momentum. Well, it abides by superposition. That's also right. Yeah, superposition. So you can add it vectorially with other momentum in the system, and that's actually how you get the total momentum of the system. Is if you have a system of particles like our solar system, right? Like you know, I guess if you want to define the angular momentum of all the particles in the solar system at a given moment in time, then at any point it would be the superposition of all the angular momenta of the particles of the different planets. Yeah, that's angular momentum. Now, so in this particular case, if the orbital motion is clockwise, then with the right hand rule, run your fingers like an arrow in the direction of the first vector. Orient your hand so that you can wrap it parallel to the second vector. Take a fist, point your thumb. So the angular momentum for this situation would be into the board. And just like angular velocity, angular acceleration, angular displacement, all those vectors are also defined in this way that if you want to know the direction of rotation, you take your thumb and point it in the direction of that vector, for this case, into the board, and your fingers will curl around in the direction of the rotation associated with the direction of that angular momentum. So run, wrap, point. Yeah. And finally, then, yeah. So, oh, sorry. So we can finish this up. So now that we've defined that, we can write Newton's second law in terms of angular momentum, and we see something analogous to what we found with translational motion. We see that another way to write Newton's second law for rotation. This is one valid way. The net external torque on a system is equal to the moment of inertia times the angular acceleration, or the net external torque on a system is equal to the time rate of change of the angular momentum. See how that works? Similar language to what we said with the second version of Newton's second law for linear motion. Analogous to this guy is net force equals mass times acceleration. Rotation, and linear version, net external force was m times a. And analogous over here, linear version is the net external force equals the time rate of change of the linear momentum. Yeah. Okay. So it's definitely a useful alternative. Now, there's no analogies in rotation to the third law. Don't take it that far. Net for every force, there's an equal and opposite force. But it's not true that for every torque, there's an equal and opposite torque. It's not true. In general, that's not true. So, I don't think. Actually, Um, hmm. Actually, let me scratch that thought. Um, no, that is true. It's not in general. That's not necessarily the case. Yeah. So it's just with the first and the second law. Yeah. That you have these analogies in rotation versus linear motion. Um, well, what I want to do now is continue with this line of thought and develop the conservation. Well, actually, yeah, let's go ahead and do that right now. And then I'm going to give you a different. So this is the definition of angular momentum, but we have another more, well, when we do conservation theorem, we can come up with another relationship for angular momentum, which is a little bit more practical. But this is the definition, and that gives us one equation to calculate it. But how is angular momentum? There is conservation of angular momentum. In fact, any body, like any orbital body, the angular momentum is conserved. And there's a specific criteria that is somewhat related to the criteria. Well, it's analogous, I'll use that word, to the criteria for which linear momentum is conserved. Now, I think, Raheem, if you're still there, it was a while ago, but when we were talking about it, I think I remember you were the one, somebody I think in the class got close or either answered what the criteria was for what is the criteria for linear momentum being conserved. So let's just review. We've got two conservation theorems, which there's some sort of equation, conservation of energy and momentum, linear momentum. Conservation of energy, the criteria is that only conservative forces do work on the system. Does anyone, if anyone's there, does anyone remember what the criteria that linear momentum is conserved? If you can look at this equation, and from that equation, you can determine it. And maybe that'll help jog you remember, but we derived it from there with basically a simple step. Does anyone recall what is the criteria such that linear momentum of a system is conserved?
Is it if the mass is constant and then there's no external force or no
Oh,
other force?
good job. Yes, absolutely. Assuming that well, actually, as it turns out, you don't have to make a qualification if the mass is constant because, and I know this is beyond the scope of the course. Oh, Esperanza, did you say something?
Oh, in my
So,
mind, I have like the stuff about the rockets in my mind.
yeah,
So the
yeah,
mass would be varying.
yeah. Also, good job, Esperanza. Yeah. Um, and yeah, I guess you're right. I was just clarifying based on Raheem's comment. Yeah, you're right. You're right. I guess what I want to clarify, and you wouldn't have any way of because we didn't go over that, and it's not kind of the focus of the course to go into that. But I think I did show you that if momentum changes, it gives you a force-like term called thrust. So it's kind of overkill to say if the momentum change, is constant, because if it does change, it's still going to be it's still it is that true? Yeah, I guess even if even if the mass changes, and it's a little bit hard. We have to kind of go into it to talk about why, I think, so that it becomes a bit more intuitive. But as long as there's no external, yeah, so yeah, just that, yeah, I guess even if the mass, so if there's no external force and the mass does change, linear momentum can still be conserved. And the rocket problem, although it might seem counterintuitive, is actually an example of that. And you might think, well, how can the rocket go up if there's no external force? Well, it's because the momentum is conserved. And because it's kind of like when you're standing on ice, right? Let's say that I have a mass here and I'm on ice or on a frictionless surface. If I actually better would be the recoil of a gun, right? You got a big bazooka or something like that and you shoot it. So you recoil, right? You do that, but you don't move. Why? Because there's net external force on you, keeping you from moving. It's the friction of your feet. So your body might move back, but your feet don't move. And if you could keep your body rigid, there would be a jolt, but you still wouldn't move because generally speaking, friction is going to be larger than whatever impulse force is associated with the change in momentum of the bullet leaving the gun. But if you're on ice or if you're out in space and you shoot the gun, you recoil and your body actually moves with a velocity and it will keep going until some external force stops you. So in that case, both the bullet and you're recoiling, before the gun was shot, there was nothing had a velocity and the momentum was zero. Well, because there's no external force, momentum has to stay zero. And clearly the momentum of the bullet is non-zero anymore. So if there's nothing to counter that, then conservation of momentum is violated. So that's why you move back. Because when you add your momentum and the momentum of the bullet, the total momentum is still zero. Why? Because the net external force of the system is zero. However, the mass of the system, the overall mass of the system didn't change, but you could definitely say that the mass of the gun, like there was a bullet in it, now there's not. So if you look at the individual mass of you and the gun moving back, that's not the same mass as it was before the collision. And how much mass did it lose? It lost the mass of the bullet. That's the same philosophy with the rocket problem. Most of the rocket is fuel. And even though we don't think of it as mass being ejected out, fuel, because it's burnt, it's volatile and it burns up, still that mass that was expelled out of the exhaust of the ship, through uh, through process of combustion, it still had a mass. And now the mass that's left in the ship after an instant of combustion is less the amount of mass that was burnt up in that combustion. And that continues every second. So it's because of there's a force-like term, it's called thrust, but it's really just a force associated with the fact that the mass is changing, the time rate of change of the mass is coming out, and therefore the mass is changing with regard to the overall ship. And but even in that case, even though the rocket is going up, the the net external force on the system is still zero because there's no external force. There's nothing external to the ship. If the system is the gas and the ship, then there's nothing external to that that's causing this phenomenon to occur. The only thing that's happening is the rocket is just throwing gas out of the bottom, and because there is no net external force, momentum is conserved. So when that gas is expelled with its own individual momenta, then the ship has to respond accordingly by going up in the same way that you recoil when you shoot a gun on a frictionless surface. So that's what I mean. You don't need to qualify the mass. Even if it changes, momentum can still be conserved because that mass was part of the initial system. And even after it's expelled, it's still part of the overall system. But because it now has a momentum after it's combustion, then the rocket has to have an equal and opposite momentum, which is what causes the rocket to go up.
So our
So,
only qualifier is the net external force.
That's the only qualifier, and it's kind of a pet peeve. That's why I'm spending time on it, because it's really significant. It's the kind of question you would see on like a GRE or something like that, you know. And the reason is because it's actually a fundamental property and concept. You know, it's part of the conservation there. So you don't want to just know how to use the conservation theorems. You also want to know when to use them, and the criteria is very extremely important. So yes, the criteria then that linear momentum is conserved is that if no external forces are acting on the system, then the linear momentum is conserved, period. That's it. Analogous to that then, so very good, both of you. And so what then, how could you use that terminology then to apply it to the criteria that angular momentum must be conserved? Anybody? Using analogous language.
It would be the same concept, right? Just the
Yes.
zero net external force.
Well, force doesn't give rotation, torque does. So change the wording, but keep the
Oh, so
right.
no net influence to torque.
No net external. If the net external torque on the system is zero, then the angular momentum of the system is conserved. That's right. That's right. And that's it. Those are the three conservation theorems that we learn at this level. Now there's also mass, but there's no equation associated with that, right? Like obviously mass is conserved, within systems. So yeah. And and again, we might touch on that a little bit when we get to gravity in a week or so, but all orbital motion, that's the case, because even though you have, because when you consider orbital motion, the planet is not just the system, it's the planet. Like in our case, it would be the planet and the sun. Both of those we are considered the system. In the case of the moon, it's the moon and the earth. So now that's a dual planet system, or yeah, I guess the moon is a planet. I mean, it's a moon, but whatever. So if those become part of the system, then even as the object goes around, there's no net external force, and this is, excluding the gravitational force of the sun and all that, and all the other planets. So in an ideal case, angular momentum is conserved for a orbital motion, and that's a big deal because it leads to our ability to derive and solve certain problems that we would not be able to solve if that were not the case. Anyway, yeah. So the criteria that angular momentum is conserved is that the net external torque on the system is zero. So angular momentum is conserved only when the net external torque on the system is zero. Okay. So now applying that property to equation 8, if zero is equal to the time rate of change of angular momentum, And you can kind of think of this as equal to the limit as delta t goes to 0 of delta L over delta t. So basically what I'm saying is that if delta L over delta t is equal to 0, what must be 0 in order for that equation to be true? Well, the trivial thing would be that well, first of all, you can't have delta t equals 0 because then you divide by 0, but that's not going to be the case anyway because you're talking about time not changing. We're assuming that time continuously changes. So if time changes when you're looking at a system, delta t won't be 0. So the only way that that can be true is if delta L is 0. Same argument that we made. It's not really a highly mathematical argument, but it's the same argument that was made that we use for linear momentum. So that then leads to this equation, which is a statement of conservation of angular momentum, at least one statement. But the version that I like the best is the following. And of course, if delta L is equal to 0, that means that delta L is L final minus L initial, which then gives rise to L final equals L initial or T. All right. And that's it. That's conservation of angular momentum. So when is energy conserved? Only conservative forces do work on the system. When is linear momentum conserved? The net external force on the system is 0. When is angular momentum conserved? The net external torque on the system is 0. Now, I promised you I'd give you another equation for L, which is really nice. That it's one that we kind of use for this. You can use that too, but this is what we kind of like to use. And it's a simple one. It's just converting all the linear stuff, because this is angular momentum in terms of linear terms. What does it look like in terms of rotational terms? Well, we've already got the translation for each of these, so we just put them in, and that gives us a new equation. So, assuming that L is equal to basically R times P, and when phi is 90 degrees, it's just RP. So then we just put in the other stuff. We say that, P is equal to, so that's R times mass times velocity, but velocity is, or speed in terms of its rotational terms is equal to R times omega. So if we stick that in, we have angular momentum is equal to R times M times R times omega. Well, we can simplify that. This becomes mr squared omega. And that's where we get using the general definition for moment of inertia. Here's we get the equation that you might actually be familiar with. You might have seen it before. And if you've been reading the chapter, I know you've seen it, but you might actually have seen it before coming into this class. And it's this guy. So remember, moment of inertia is mr squared. So whenever in general, and again, that also changes based on the system. So you keep that in mind. You got that chart back in chapter 9 or whatever it was when we were calculating that. But so now angular momentum is equal to I omega. Now that's not the definition, but that is a second equation from R times P. It's just the rotational version of the same thing. But equation 14, you see oftentimes expressed in terms of the rotational terms. So conservation of momentum then is oftentimes expressed as I, final omega final equals I initial omega initial. So again, conservation. And so this is the version of that you use whenever you do the problems where, like, like in the Olympics, the Winter Olympics, you got the skaters and they're twirling around and they have a certain momentum and then they put their arms in and then they go faster, much faster. That's because of conservation of angular momentum, because they definitely are applying a force to their muscles, but it's an internal force. It's their muscles on themselves. And if you assume that the ice is frictionless, which is practically is, then there's no external force. That's why that happens. That's why when you constrict, you're changing your moment of inertia. And it even makes sense, right? Because now we know that moment of inertia is change, is resistance to change in rotational motion. But what did we say? We said that when the farther your mass is away from the axis of rotation, the larger the moment of inertia. Well, the larger the resistance to change in motion. So whatever, because you already have your motion, right? The energy is in there. Somehow they spun themselves, so they started spinning. So when their moment of inertia is big, they have a larger resistance to change in motion. But as they bring their mass closer to the axis of rotation, which is down the center of their body, their moment of inertia is decreasing, even as that's happening. And you can see it. It's like, they start to spin really, really fast. In fact, it's not a linear relationship. Why? Because, can I show that here? I think because, well, yeah, it's not obvious, but basically, I guess because the kinetic, yeah, I don't know. I don't want to confuse with energy, but yeah. So you can see that's what happens as you constrict and decrease the moment of inertia. The angular velocity increases quite significantly for most of those scenarios. So that's it. That's a combination of understanding of conservation of angular momentum and the same thing with orbital motion. Like. Although there would have to be an external force in that case, so it wouldn't be conserved. But so a couple things to be careful of. Oh no, yeah. So it's the same thing. Like, yeah, that would actually be. So if you had like a rocket and it's going around a certain orbit, and then it fires its engines and goes out into a closer orbit or a farther away orbit. If it comes into a closer orbit, it's going to have to go. It's tangential speed. Well, actually, it's angular speed and tangential speed, radial speed will have to be, or tangential speed will have to be faster to maintain a lower orbit because of this. And if you go farther out, then you would be going slower to maintain a larger orbit because of conservation of angular momentum. Now, the planets don't normally do that because they don't have any internal combustion. And usually, if they change their orbit, it's because something hit them. And if that's the case, you can't use conservation of momentum because the momentum wasn't conserved. If an asteroid comes in and hits the moon and knocks the moon out of its orbit to a larger orbit or a smaller orbit, you can't use conservation of energy to calculate those properties because there was a net external force, and so therefore there's a net external torque associated with that issue. The other thing you have to be careful about is, let's go back to the skaters. Oftentimes, people are tempted to apply conservation of energy, even when there's no external force, but energy is not conserved. That was a big one. That's one of the situations that would trip me up, that I used to get tripped up on when I was an undergrad. So let's say you got the skater, and the skater is doing the snare that I talked about, right? They bring their arms in and they twirl. Because conservation of energy is something that you're already familiar with, your intuition might be to think that you have an option, either conservation of energy or conservation of angular momentum, because you just learned this. Maybe you just want to do the energy, or maybe you just don't think about it. Maybe you don't think it matters. But it's deceiving because you say, okay, well, what's the idea? The criteria for energy being conserved is that no external, only conservative forces can act on the system. Well, if gravity is not doing work on the system because gravity is vertical and is still counterbalanced by the normal force, And if the ice is frictionless, you might think, oh, well, there's no external forces there's no non-conservative forces acting on the system. And so they bring their arms in, and I can do conservation of energy, and I can use that to figure out the new angular velocity and the new tangential velocity. But if you apply conservation of energy and then apply conservation of momentum, you don't get the same answers. Now, your hint is that definitely angular momentum is conserved in that case. I just told you. But why is energy not conserved in that scenario? The scenario where skater is, let's say, Michelle Kwan, who's my favorite, skater of all time, and is, does that move where they're doing the spin, they bring their arms in, and they go to a new angular velocity, and you use conservation of energy using the rotational kinetic energy, 1/2 I omega squared, and set that up, one equals the other, and then you solve for the new angular velocity, you will not get the correct answer because energy is not conserved. So can someone tell me why energy is not conserved in that scenario? Just think about it while I get my tea, and you can answer at any time. Oh man, I did not realize it was 4:30. Wow, I just looked at the clock. Well, let me tell you then, and I'll let you go.
Is
I'll
it
just,
because uh the energy is expended in I guess like doing the work to increase their inertia where they're
yeah,
spinning faster?
awesome, great answer, dude. Yeah, you're burning calories, right? You're using energy. Your muscles use energy to extend themselves, and you don't get that back, right? It's work, right? Like you're sweating, it expels, it turns to heat, it does all those things. Chemical energy is being converted to heat, and yeah, and there's friction on your muscles. That's why you sweat. Yeah, that's energy. You don't get that back. So, yeah, internal energy is being expelled. So you have to consider that. Have to think about that. And it's the same thing for the ship. When the ship changes orbit, even on its own accord, that's chemical. It's firing its rocket boosters, right? And so that's coming from whatever the fuel is, whether it's chemical energy or nuclear, whatever. It doesn't matter. No matter how advanced the energy propulsion system is, it's doing work. Like you said, that's a great way to think about it. And if it does work, and that it work did something, you don't get that work back. And so even under those circumstances, even if it's not an external force doing work, it can be internal forces doing work. But those forces are not conservative. Burning calories is not a conservative force. Remember, like the muscles, they're kind of an easy cheat is that if there's got to be if there's got to be no contact on any level for the force to be conservative. Technically, when you got levers and mechanical systems, there's contact all over the place, even if it's inside your muscles and your ligaments and stuff, right? Contraction, the fibers are rubbing against one another, like, I mean, that's kind of yeah. So, yeah. So you're going to find examples in the book. I can let you do that. We could do one in class, but sometimes they have Einstein on a pedestal with some bars or something. A lot of books have that, or a lot of books have the skaters, and it's so you can test that. And in fact, they might actually have you test it in the examples where you set up a problem like that, apply conservation of energy or momentum, and get the answer for the new system, the new angular velocity system. Then have you compare that with conservation of energy, and you see that you don't get the same velocity. So yeah. So that's angular momentum. It's a new concept. It's something that doesn't really, well, it's analogous to linear motion, but just like momentum was a new quantity, this is also technically a new quantity. But yeah.